Welcome back after lunch. Hope you all enjoyed our lunch. I know it's very difficult for both audience and speakers to have a post-lunch session. I'm sure our galaxy of speakers in this session will definitely make it interesting session. So now we'll move on to the third session, Aerospace Materials Technologies. In this we have totally 5 lectures delivered by our experts. So first lecture will be delivered by Dr. Lakshmi, Principal Scientist, Surface Engineering Division, on thermal insulation coatings for aircraft, followed by eco-friendly corrosion protective coating for aircraft by Dr. Sri Prakash, again Principal Scientist from the same division. And third lecture will be high temperature coating for gas turbine engines by Dr. Senthil Kumar, Principal Scientist, SED. And followed by next generation eco-friendly coatings for industrial application by Dr. Selva Kumar, and followed by CFSIC CMCs for aircraft brake disc application by Dr. Uday Kumar, Deputy Head Material Science Division, CSIR NAL. And finally we have indigenous carbon fibers for CSIR NAL by Dr. Tarun Kumar Pradi, Head CCFE Carbon Fibers CSIR NAL. Now I request Dr. Lakshmi to deliver a lecture.
Good afternoon, everyone. The technology I shall be discussing now is the thermal insulation paint coating technology. This paint coating technology developed in 2023 caters to the requirement of aircraft's requirement, that is particularly for providing thermal protection and insulation on aircraft surfaces against impingement of hot air with high mass flow rates. So the motivation for carrying out this activity at CSIR NAL is the requirement in our own in-house program. Our CSIR NAL developed Saras aircraft had a similar issue of undesired heating at the rear fuselage areas, and to address this heating we had to develop a paint which was compatible with the existing paint layers. So this paint suits for temperatures up to 150 degrees centigrade against hot air of mass flow as high as 1.1 kg per second per stub. This is the photograph of the test rig facility, the gas generator test rig, which was used to evaluate the coating. Now why this, the coatings were tested at this facility? Because we had to check how effective the coating is against providing the thermal insulation against not just the hot air, but also it had to withstand the high mass flow rate. So we generated the hot air with the required mass flow rate in this test rig. You can see the samples mounted on the sample holders over here. So tests were carried out on the coated samples against the uncoated samples. They were carried out on both aircraft grade aluminum alloy and CFRP substrates. The coatings have undergone rigorous testing. As we can see over here, they are listed here. So they have been tested for their environmental durability, like accelerated weathering test as per ASTM G154 for 500 hours. And after the test, the coatings have been tested for its adhesion onto the substrate as well as for its thermal insulation behavior. The coatings were tested for its intactness using C-scan technique. Followed by the coatings were tested for driving rain, salt fog, flammability, sand test, dust, cath, and contamination by 3 different kinds of fluids which are commonly encountered on aircrafts. All these tests were carried out as per relevant military standards, RTCA and ASTM standards. Further to this, the coatings were also tested for its mechanical durability. So they were tested for its intactness towards vibration test and also pull-off adhesion test. Adhesion is a very, very important factor for these coatings onto the aircraft to have long service life. So in the next slide, I shall detail you a little on that. Further, the coatings were also highly stable against thermal tests which were carried out, including thermal shock, thermal stability and thermal cycles up to greater than 8,000 cycles. So as said, adhesion was a very important factor to determine the service life of these aircrafts. So adhesion strength of these coatings were determined using the dolly test as per ASTM standard, using dollies of size 20 mm. Here the coated samples, the thermal insulation coated samples were tested against the conventional samples. That is the substrates with the normal, the conventional aircraft grade BS2X34 polyurethane and yellow primer coatings. So the tests were carried out as per the standard, and it was seen that the adhesion strength of the coated samples were much higher than that of the regularly seen values for the normal samples. So that is why these coatings, I can say that they had very good pull-off strength for these samples compared to the regular coated samples. And all of the tests what were listed in the previous slide were all carried out in NABL accredited laboratories and witnessed by inspectors from the certifying agencies. So this also was a very important test which we had to do, wherein we carried out the flammability test using the horizontal burning test method. So here, as per the requirement, the coating had to have a linear burning rate less than 75 mm per minute. And we see that the developed coatings had almost half of what was actually required. Therefore, the coatings also qualified these tests. So the salient features of the thermal insulation paint in brief, if I have to say, so this paint is suitable for the applications for providing thermal insulation against hot air for temperatures up to 150 to 180 degrees centigrade. The density of the coating is very low, which is about 0.85 gram per cc. The paint is developed using locally available raw materials. The deposition technique is also very simple and doesn't need any sophisticated machineries. Hence, it can be easily adopted into the industries. So, since the method of deposition is a simple spray technique which can be carried out at room temperature, there is a lot of ease in controlling the coating thickness and also on deposition of the paint on complex shapes. So, since it is a spray technique, it is also possible to carry out local repairs on site. So, it is non-combustible with extremely low flame spread. It is suitable for metal, concrete and composite because this paint has been proved on both aircraft grade aluminium alloys as well as carbon composites. The paint is compatible with the epoxy as well as the PU paint. No additional waterproofing is required and it is resistant to regular wear and tear. So this is a photograph of engine stub wing coated with the CSR NAL developed thermal insulation paint. So this indicates that it is very easy to scale up the coating onto even a curved surface. So the paint has been accorded by pre-production clearance. The paint has been accorded with pre-production clearance by Semilac in August 2023, and we have taken up activity to put it on the aircraft and see its behavior. This technology is available for TOT. Thank you.
Thank you very much, madam, for keeping your presentation short and covering a thermal insulation technology developed at NAL. If you have any specific queries from industry partners, we'll be happy to answer. So, if there are no questions, I once again thank Dr. Yeah, we have one question.
Yes, yes.
Mic, hand over mic.
You are told about the burning test, right? So, what's the standard you follow for the burning test?
Actually, we have followed UL 94 standard, which has an equivalent ASTM standard also.
Okay. Thank you.
It is UL 94.
UL 94.
Yes.
Thank you, madam, for your interesting talk. Now, I request Dr. Sri Prakash to deliver a lecture on eco-friendly corrosion protective coatings for aircraft.
Good afternoon, everyone. I would be talking about two technologies, eco-friendly technologies. that we are going to be used in aerospace applications. First one is the eco-friendly anodization for corrosion protection of aircraft aluminum alloys. You know that in aircraft and in engineering applications, aluminum alloy systems are used because of their low weight. But these alloys like 2024 or 6061, which are being used in aerospace, are prone for the corrosion. For instance, in aerospace, when you have on the top of aluminum sheet, it is usually protected for corrosion by using anodic layer, and further on the top of it we will apply primer, and on the top of it further the top coat. This chromic acid anodization, which is conventionally used because of its high corrosion protection, and it has very good adhesion to the primer, and it leads to minimal reduction in the fatigue strength. But unfortunately, this chromium, hexavalent chromium, that is used in the development of this chromic acid anodization is highly carcinogenic and toxic, and it has to be phased out at the earliest. According to one of the forecasts, a likely sunset date for this hexavalent chromium containing chromic acid anodization is 2026. So the need of the hour is to develop an alternative anodization process which will give the performance level equivalent to that of the conventional chromic acid anodization. So people have been trying throughout the world, finding out a suitable alternative anodization. For example, sulfuric acid anodization, boric sulfuric acid anodization, or tartaric sulfuric acid anodization. These are the alternatives that have been envisaged. But most of the time, due to the lack of enough corrosion protection, they are usually sealed with hexavalent chromium containing sealant, which is again undesirable. So keeping that in mind, we have developed at NAL an alternative process, which is a modified tartaric sulfuric acid anodizations, and we have sealed it with an eco-friendly chromate-free formulation. And we have evaluated this alternative coating for a variety of tests. For example, it is qualified as per as MIL A8625F, that is generally the standard which is used for the evaluation of even the chromic acid anodization. So, first and foremost, it was tested for the corrosion testing, and it was placed in a conventional salt spray testing, and we have evaluated it for ASTM B117 based on that, and we have shown that it qualifies more than 2,000 hours at par with the conventional chromic acid anodization. Apart from that, we have tested its compatibility with the primer through an adhesion test. You can see that it is very good adherent with the primer, and the flexibility is very intact. There is no peeling of the coating when you drop a kg ball on the top of it. And adhesion with the primer on the right side, you can see that it's very much intact. So, foremost is that it is totally free from any of the ROHS or any of the hazardous chemicals, and is totally ROHS and REACH compliant. And what has further boosted its performance, this one, is that it has qualified more than 15 months in the coastal environment, which we keep in the Mandapam near the Rameshwaram. So, proving that it's a viable alternative for the conventional chromic acid anodization. This technology has been patented throughout the world, European as well as the US and in India. And it's you don't need any extra facilities when compared to the conventional chromic acid anodization. Same setup can be implemented even for the tartaric sulfuric acid anodization. And in terms of the costing, it's at par with the conventional process. And we have obtained this one semi-lag pre-production approval. Recently we obtained that, and we are going to implement that for our in-house aircraft programs. And soon it will be implemented in Hansa NG, our own in-house aircraft programs. And we are also in conversation with some of the industries for this, for the technology transfers, and also with HAL we are in deliberations. So it is presently available for the technology transfers, and the technology readiness level of this process is 7. So it means it's already, it has been a proven technology. And you can see in some of the components which have been coated with the TSA anodizations, and these are the Hansa components. Sooner than maybe within 2-3 months it will be implemented in the next aircraft system. The second technology, eco-friendly technology, which I would be talking about is a zinc-nickel process. It has been developed as an alternative process for the cadmium. Cadmium coatings are generally used in for the corrosion protection of the high-strength steels because of its excellent corrosion resistance, and it provides corrosion protection through the sacrificial coating, and it has a very low coefficient of friction. That means it has a high lubricity, and it does not result in any kind of reduction in tensile or the fatigue strength. But unfortunately, it is again the toxic and carcinogenic because we use cadmium in the process. There is a cyanide in the process and also the hexavalent chromium. All these three entities are very carcinogenic and it has to be limited. So we have developed an alternative process, zinc-nickel process, and it has been evaluated extensively as per the AMS standards, and its thickness is in the range of 10 to 14 microns. It has been evaluated for the adhesion test through the scratch test and through the bend test. You can see that there is no peel off of the coating, and its compatibility with the primer and the PU has been established. And this is the setup we have for the development of the 500 liter facility that for the production of the zinc nickel coatings. So these are some of the salient features, and the thickness is in the range of 15 to 18 microns. And the corrosion resistance more than 500 hours of salt spray and without any kind of redress formation, which is as per the requirement of AAMS 2417J. And adhesion is excellent. It has been evaluated as per this standard, and it has qualified more than 200 hours of hydrogen embrittlement test, and the lubricity is comparable to the cadmium. So we have obtained the pre-production approval from RCMA, Semilag, very recently, and we are going up for the next, like for the airworthiness certification, maybe within 6 months or so we'll be getting that approval. So the costing is at par with the cadmium even for this zinc nickels. And wherever high strength steels are used, we can use this for the corrosion protection as a replacement for the cadmium. And post airworthiness approval technology will be potentially transported in aerospace industry. If anybody is interested, they can take up this technology and can be used as an alternative for the cadmium. And there are no technologies as such in India now for as a replacement for the cadmium. It's a one of the kind. So I strongly believe that this can completely eliminate the cadmium in the corrosion protection applications. Thank you.
Thank you, Dr. Prakash, for your insightful lecture. If you have any specific queries to the speaker from industry partners. Okay, if there are no questions, once again, thank you very much for your informative talk. Now I request Dr. Senthil Kumar to talk on high temperature coatings for gas turbine engines.
Good afternoon, everyone. So today I am presenting our technology on high temperature coatings for gas turbine engines. So as aerospace laboratories, we have our own indigenous programs on the gas turbine turbine engines, and whatever the required coatings, everything is developed indigenously at our lab. As you are aware, it is one of the most crucial components of aircraft, and for that we need to have a very stringent requirement, and we have developed the coatings adhering to those requirements, and it uses a wide range of coatings, high temperature coatings. And as you see, the gas turbine engines, there are the different temperature zones ranging from the 300 to 400 at the inlet to up to 1200 degrees centigrade at the outlet. So we have developed different coatings for different components. So these are like thermal barrier coatings. So wherein thermal barrier coatings for this turbine engines, and then environmental barrier coatings for composites components, and erosion resistance coating mainly for the compressor components. And we have various IP patents in this area. And the salient features are these TBCs are compatible for a high temperature of 1100 to 1200 degree working temperatures, and wherein you can achieve up to 120 degrees centigrade temperature drop so as to protect the bare metal from the very hot zone. And it has a very good thermal durability and low erosion rate. And our EBC coating, that is environmental barrier coating, which is meant for this composite components, are of moisture resistance, and it has also a very good thermal durability. And the other coating is erosion resistant coating for our compressor blades. So these are all made by the sputter coating techniques, which has a very good ultra small grain size, stress control uniform coatings, and it have both ductile, brittle, balanced nature. And we have also transferred on technology based on this. That is for plasma spray coatings, whatever the powder required has to be flowable. Those flowable powders we have made by our own process, indigenous process by spray drying, and this process has been patented and also transferred to industry. So as you are aware, this gas turbines, there are many degradation issues in the typical gas turbine components, ranging from the hot corrosion, erosion, and the CMAS attack. The CMAS attack is like a volcanic ash which consists of calcium, magnesium, aluminosilicates, which can react with your these components, and then that will degrade your turbine blade components. So here you can see these gas turbines having the range of temperature zones ranging from 350 to 400 degrees centigrade to 1200 degrees centigrade. So we're developing different types of coating for these components. So one among them is the thermal barrier coating. So our basic strength is we have all the inherent requirement for the coating process, like plasma spray facilities, spotter coating facilities. All those facilities are we have, and we have state-of-the-art characterization facilities for these coatings, like thermal cycling, and there is a unique facility which you can find only at NAL, like this combustor rig test facility, where you can test these coatings in a typical gas turbine conditions and simulated mass flow and pressure conditions. And these coatings and other strengths are, we have expertise in developing the indigenous compositions, whatever required for the coatings. All these compositions are in-house synthesized, and whatever required for the process, like a flowability and all, we made by different process, like chemical precipitation routes, spray drying, and the combustion synthesis methods. So these coatings are tested for typical aerospace conditions, and it undergone all sorts of testings, stringent testings in our test rig. And you can see we have made the wide range of thermal barrier compositions, ranging from doped yttria stabilized zirconia and ytterbium doped zirconiates, Garlock pyroclose, and all. And the uniqueness of these coatings are that it has a very low thermal conductivity, which is one of the important property for this thermal barrier coatings. And it's worth mentioning here, our thermal conductivity are in the range of 0.5 to 1 watt per meter Kelvin, wherein the commercial YSE coatings are about 2 watt per meter Kelvin. And we have tested for thermal cyclings, and even now we have even achieved more than 100 thermal cycles in these coatings, and our erosion rates are one order of magnitude lower than the commercial coatings. So the other one is environmental barrier coatings. So in the next gen engines, the people are also using this composites, SiC composites components in the aircraft engines. So it requires different type of coatings, because the corrosion problem is altogether different comparing to the metal-based components. Here at a high temperature, in the presence of water gas, this SiC matrix will get degrade over the time by hydrolysis. Further, a different type of coating has been evolved. So here you can see these are all ytterbium silicate based coatings. So it's once again a multi-layer coating. Here you can we have also given YAG based CMAS resistance coating. This is mainly to protect the engine components from the CMAS attack. That is mainly by this volcanic ash. And here you can see this coating is very much durable comparing to the bare CMC substrates. And we are also developing developed a third generation erosion and corrosion resistance nano coatings. This is by the sputter coating process. That is the DC pulse laser sputter coating process. Here you can these coatings are developed mainly for compressor blades. So wherein the solid particle erosion is a major degrading issues. So of the components here. The solid particle erosion, the major issue, which creates the engine, which decreases the engine efficiencies and increases the CO2 emissions and other types of engine failures. So here we have developed this TL nitrate-based coatings, that is TIN, and this is once again the multi-layer coating by the sputter coating process, and this is have very good erosion resistance, about 74 times higher than that of bare substrate, even at the speed of 30 meter per second. At higher speed also, that is higher erodent speed also, the erosion is reasonably good here. That is we achieved up to 12 times higher than the bare substrates. And it also has a very good corrosion protections. And further to that, we have also come out with this nanoporous based coatings. This uniqueness of this coating is it can absorb the erodent energy to some extent, and by the way, it is improving the improving the erosion resistance. So in this case, even we have realized. We have realized about 18 times higher erosion resistance than the bare titanium alloys substrates. So with this, we have these coatings have ability to withstand the high temperature, erosion resistance, and corrosion resistance. And not only in aerospace applications, it can also be used for many industrial and automobile applications. For example, this same plasma spray coating process has been used for our fuel cell coatings. That is for coating the spinel oxide on the metallic substrates. That is there, it is a SS substrate. So wherein the requirement is slightly different. So what I want to mention here is this is not just aerospace, it has many applications. If any industrial partners come forward, we are ready to customize these coatings as per their requirement. Thank you.
Thank you very much, sir, for highlighting high temperature coatings work at NAL. Do we have any queries? Yeah, we have.
Hello, sir. So the thermal coating, will it be providing resistance from oxide or combustion
Yes.
related corrosion effects?
Certainly, because basically this is whatever this thermal barrier coating is developed for turbine blades. Yeah. So after this combustion chamber of the this GT, gas turbine engines. So it will mainly face the combustion products. So whatever the hard corrosion I am saying is mainly because of these combustion products. So in presence of combustion products also, it can protect. That's what we have proven.
Okay, thank you.
Yeah, thank you.
So one more question.
So thanks for answering one of my questions on the combustion liner characteristics. So whether you have already exposed this coating to that combustion
Yes.
or Up to what temperature?
Yeah, we have our dedicated burner rig test facility at our propulsion division, wherein we are exposing up to 1200 degrees centigrade. This coated materials, it is mounted on the rig, specific rig, and then it is exposed up to 1200 degrees centigrade. And we are measuring what is the temperature drop, and even the post analysis also we are doing.
Yeah, you have done a thermal cycle as well, right?
Yes, we are doing thermal cycle as well. So thermal cycling, there are some standards, ASTM standards, wherein we have to go up to certain temperature, typical to the, in the gas turbine engine condition, 1100 degrees centigrade, and then we will be cooling suddenly. And 1 second, so like that we have went up to more than 100 cycles.
On a question, as the hydrogen combustion is coming into a forefront.
Correct.
So how do you see this coating compatibility or embrittlement issues?
Okay, so one important thing in the hydrogen, when you are using hydrogen, certainly the engine temperature is going to be very high. Okay, we had also a discussion with Ashok Leyland. So they are also now coming with H2ICE. Internal combustion engine, hydrogen-based internal combustion engines. We are also in discussion. So one of the things we come to know is when even if you are using natural gas, compressed natural gas, your engine temperature is going to be very high. So even for that, they are using these kind of coatings on the enclosure, protection enclosure. Otherwise, the radiation will be very high in the vehicle inside and out. So they are using some kind of coating on the envelope. Engine cover and all. So this can be tried out very much there.
Thank you. On last question.
Yeah.
So you talked about the thermal conductivity. You are
Yeah.
getting around 0.5 to 1 watts per meter.
Yeah.
So means you have a test setup for that to arrive at, or how did you?
Yes,
got that
actually, this is we have our sister lab, SICRI Karaikudi. So we are testing because we always work together. So we are sending the samples there and getting done there. This thermal conductivity measurements.
Okay, thank you.
One more question.
So normally turbine blades and other base materials, they expand because of temperature rise and all.
Correct.
So will this be able to expand along with the material without cracks?
Correct. Correct. So for that reason, we are using specialized bond coats. Okay. So these bond coats will take care of this thermal matching. Both will have different thermal expansion coefficient. So, and also we are experts in developing the indigenous coating to adjust this thermal expansion coefficient as per the bare metal. So with this we have addressed that. Otherwise it will spall. The reason we are doing thermal cycling is mainly to check that whether that spalling is happening or not.
Okay, so for every base material, this particular has to be customized accordingly.
Because the TEC will vary. The thermal expansion coefficient of a material will vary. Accordingly, we need to adjust the thermal expansion coefficient of the coatings which we are applying, which we have already expertise in that. That at least for this aerospace alloy, we already developed the range of aerospace like Inconel, Nimonic, and even for SS, we have developed different type of coatings like SS430. We need to see if you have any specific metal composition, we will see. If TEC falls within this range, no issue.
So normally what is the base material for turbines this particular thing is?
Yeah, so usually this Nimonic 90, they will go for turbine blades. And for casing and all, they will go for Inconel 718 like that. Okay.
Thank you very much, sir, for your wonderful talk. Now I invite Dr. Selva Kumar, a Principal Scientist, SCD, to speak on next generation eco-friendly coatings for industrial application. Nishad. This is your PPT. Yes, sir. Yeah.
is friendly. I'm audible? Yeah. So let me start with a brief introduction why we have developed this environmental friendly Nalsan next generation coating technology for solar water heater applications. So in the late 1980s, NAL developed Nalsan spectrally selective coating for solar water heater application, and the technology has been transferred to 29 industries. However, this coating is an electrodeposited black chrome coating, and it contains hexavalent chrome, which is an carcinogenic, and its disposal is a challenge. So hence many industries, they were approached us to develop an eco-friendly and easily scalable coating technology, and which at the time the technology was not available in the country. So we, towards this, we developed this Nalsan next generation coating technology, which is cost effective, easily scalable, and the major advantage is that it is completely environmental friendly. So during the period of 2019 to 2023, we have developed this coating, and the major advantage is that the coating has a very high solar absorptance and very low thermal emittance, means it can absorb the solar energy and it can convert it into thermal energy at a very high rate. And the major advantage, one of the major advantages is that we have not used any volatile organic compounds, and it is a completely environmental friendly coating, and it is an ROHS and REACH compliant. And the coating concept has been protected under an Indian patent and also an international patent, and also a trademark is filed under the name of Nalsan NG. The technology has been transferred to Messrs. Supreme Solar Private Limited, Doddaballapur, in the month of February. So the coating concept is designed in such a way that, as I mentioned before, no hazardous chemicals were used and no volatile organic compounds were used. And the spectrally selective coating consists of two layers. One is the absorber layer. For absorber layer, we have mainly used graphene oxide as the base material, and we have used water as a solvent. And we have added few more other additives, and we made this coating as an absorber coating. Generally, graphene oxide is a black body absorber. That means it will, whatever it is absorbing, it will emit everything. Whereas what we have done is that by adding few additives, we converted this black body absorber into a spectrally selective paint. And the second one is that inorganic protective layer solution. There also we have mainly used the inorganic material as a base material, and there also we have used water as a solvent. We have not used any volatile organic compounds. So these spectrally selective coatings, using that, we achieved absorptance of almost 93% and emittance in the range of 30%. The coating also has a very high thermal stability up to 175 degrees Celsius for 600 hours. And the optical properties of these coatings are almost matches with our existing Nalsan coating technology. So to utilize this coating for practical applications, the coating has to qualify various environmental tests, and in addition to that, it has to undergo this humidity test, condensation, corrosion resistant, all those tests. And all these tests was carried out under ASTM and International Energy Agency standards. We have tested these coatings by Enable Accredited Labs. It's a third-party agencies. They have evaluated and they have provided the certificate. The two major tests is that one is the ROHS test and the REACH test. So these two tests will give you the idea whether any hazardous chemicals are present in your coating or not. And this test has been done at TUV Greenland, and they have provided that the coatings are ROHS and REACH compliant. The ROHS test clearly shows that there is no heavy metals, phenyl compounds, and phthalates present in the coating. Whereas the REACH test is very crucial. It is having a 223 substance of very high concern. Even if you are simply using an acetone in that coating also, that it will not qualify the REACH test. So it clearly shows that we have mainly used all inorganic materials to get this technology. As I mentioned before, we have used mainly water as a solvent. So this coating has qualified the VOC test. And this corrosion resistant test, which mainly using the sulfur dioxide gas, this test facility is not available in the country. So for this test, we have sent the samples to TUV Greenland, Germany, and the coating has qualified this test. So the major test is that the conversion efficiency test. The conversion efficiency test is nothing but how much is our coating is absorbing the solar energy and converting it as a thermal energy. To do this test, we have prepared a solar water heater panel with the help of the private industries, and this panel was sent to Regional Solar Energy Testing Center, Madurai, and they have tested this coating for almost 2 months, and they provided a certificate. The conversion efficiency of the coating is almost around 70%. Whereas when compared to the Chinese evacuated tube collectors, where recently it is available in the market, the conversion efficiency is only 55%. Whereas the major advantage of using our coating is that the conversion efficiency is 70%. And based on the test results, we found that the service lifetime of the coating is almost more than 20 years, whereas none of the Chinese evacuated tube collectors can give that guarantee that the service lifetime is more than 20 years. They are not able to provide, because this is a glass receiver tube and the damage is very much evident. So that is why this advantage of this flat plate collector is that the service lifetime is more than 20 years. Even though this technology we mainly developed for solar water heaters, this technology contains major 3 products. One is that indigenously developed GO powder. This GO powder we have used for making this absorber paint, whereas as many of you are aware, this graphene oxide has various other applications. This graphene oxide can be used for solar cells, it can be used for chemical sensors, it can be used as a radar absorbing material, it can be used for even supercapacitors, battery electrodes, and applications are plenty. So here we have mainly used this for water heaters, whereas we can, based on our requirement, we can modify this GO powder based on our applications. And the second one is that solar absorber paint. This absorber paint, now here we are using it for solar water heaters, whereas the same paint can be used for solar cooking applications, solar drying, as well as solar desalinations. And the third one is that the inorganic protective layer solution, which mainly we have used to qualify the environmental tests, like for high humidity, high condensation, we have used this protective layer. So this coating also can be used for various other applications. And the technology, as I mentioned before, it has been already transferred to Mesa Supreme Solar, and in another 10 days time, they are going to start the production line. And it is very much available for commercialization. Thank you.
Yeah, thank you very much, sir, for your insightful talk. Are there any questions for the speaker? Okay, if there are no questions, we will move on to the next talk by Dr. Uday Kumar, Deputy Head, Material Science Division. Thank you. I'll leave it there. Yeah, he will come. That is pointer. Yeah. Okay.
Good afternoon to one and all present here. So now I'm going to give a brief presentation on 2 technologies. One is basically the continuous fiber reinforced ceramic matrix composites through CVI technology, chemical vapor infiltration technology. It is one of the process, gas phase process, where we can convert the preform into a final product for various applications. The salient features for this technology is that the temperature and pressure involved is very low, so that it doesn't damage your reinforcement. And the reinforcement can be anything, like carbon fiber. I think my friend Dr. Tarun is going to address on that. Now, and also we can use the silicon carbide fiber or oxide fiber. So any fiber can work as a reinforcement. And in the low temperature itself, I can get the phase which we wanted in the CVI. That is and another thing is their strength to weight ratio is very good. Because of the low density and high Young's modulus. So the products which we have made already using this CVI technology, you can see here. The centermost is the aircraft brake disc applications, where we take the carbon fiber as a reinforcement and we process through CVI, and finally we get the product. And similarly, a lot of gas turbine engine based, gas turbine exit nozzle side, especially the conversion flap sleeve, and also some of the applications like the hypersonic application for hypersonic cruise missile applications, especially the wing leading edge and nose tip and so on and so forth. And also nuclear applications also is there, that is your CSIC fuel tube. So basically the applications point of view, it is almost you can find applications in all strategic sector. starting from the aerospace. Aerospace, if you take the brake disc is one of the main applications, and also the your helicopter brake disc also we can make. And another thing is that in the gas turbine nozzle side, especially in the static side, like nozzle, conversion in a nozzle side, like flaps, like divergent flaps, convergent divergent flap systems, where we can use these composites. And recently, this composite has been used in the rotating side also, that is in the LEAP engine, linear edge propulsion engine, which is the breakthrough made by Safran in combination with the GE. So that is a fantastic engine with a lot of high reliability and efficiency and all. And also see this application. This also finds application in the energy sector. Basically, the fission side fuel tube and fusion reactor. There is a SiC composite where this can be used as a flow channel insert. And the facility is required for this to absorb. Basically, one has to have the CVA reactor, which has got a 1400 to 1600 temperature capability. Pressure capability should be 1 to roughly about 300 millibar pressure, and power capability should be 400 to 500 kilowatt. And also the company should have a team of engineers and technicians with the little bit of experience in handling of chemicals and gases. So the CVI is nothing but it's a chemical vapor infiltration process where we bring the gaseous reactants and allow them to infiltrate the heated porous preform and allow them to react at high temperature and low pressure, and it forms a refractory solid. And if you keep on do this, the whole preform, which is porous, which will be converted into a tough composites. Basically here you have, this is actually the preform where the gaseous reactants is infiltrated via chemical diffusion, and the reaction is taking place. Especially when you start with the preform will have a lot of free surface area will be more. So first it starts with every individual fiber will coat. Then after some time the inter-fiber bundle will be coated. And finally, if you keep on do this reaction, finally you end up with the full-fledged composite. So this is the densification rate. So typically about 300 to 400 hours of infiltration is required to get almost 88 to 90% of theoretical density. So this is a typical the CVI process, where here you have the, in addition to the uniformity, to improve the uniformity, we are also rotating the whole component while the reaction is taking place. So that ensures the uniformity of my product. And this is the process and schematic where you bring the reactants in the form of gas along with the carrier gas, then allow them into the porous heated free form, then the chemical reaction takes place, and the unreacted chemicals, gases, unreacted chemicals, and also the byproducts which has to be sent along with the exhaust. So this is the typical process flow. So this is the CVI reactor facility which is available at CSIR NAL, established in 2005 with the support from DRDO to the tune of 8 to 9 crore, which is having the temperature capability of 1400 degrees centigrade and pressure capability of 1 to 300 millibar. And this is the process, typical process. First you start with the preform making. Here basically we take the 2D fabric and then they cut into a fabric layers, then stack 90 degree and 0 degree and 90 degree and repeat till you reach the thickness. Then you also stitch in Z direction so that the interlaminar shear stress will be more. And once the preform is ready, then it will be put it into a reactor. And first we will go for the interface coating by cracking methane. So there I get the pyrolytic carbon. And in some cases boron nitride also we can take. BCl3 and ammonia will be reacted and get the boron nitride. And finally the matrix CVI by taking methyl trichlorosilane, which is decomposed at high temperature to get silicon carbide. So this is a typical process flow. And this SiC means silicon carbide fiber is used as a reinforcement, rest all same. So we have characterized in terms of physical, thermal, mechanical, the relevant properties. And typically you can see that tensile property of this 6-SiC, where the pyrolytic carbon interface is around 90 nanometer thickness, where you get a very good pull out. That means my fracture toughness in the order of 20 MPa root M. And in this case, boron nitride interface, here that interface engineering so important. You can see these two microstructure. One is that boron nitride interface is applied, and just we finish making the composite, but finally end up with a brittle material. Having spent a lot of money and time, finally we end up like a monolithic failure, monolithic ceramics. So then we did some interface engineering like intermediate retreatment, and we removed the unreacted and trapped methane and ammonia and BCl3. Then we could end up with a very nice pull out. So you can see the load displacement curve is almost mimicking my metallic behavior. And this is C-SiC. C-SiC means carbon fiber is embedded in silicon carbide matrix. Here also we have characterized almost all the properties, and you can see the flexural curve. It's not a sudden failure, it's a pseudoplastic, and tensile also you can see. So this is with respect to the first technology. So these are all the components which we have developed. The second technology is that so far whatever I explained the CVI, it is a time consuming process, 300, 400 hours. So now how to reduce the time? So to reduce the time, we have taken up the process called the hybrid process, where we want to complement CVI with other processes like polymer impregnation and pyrolysis, and also liquid silicon infiltration process. So thereby we can reduce the processing time to something like 40% to 50% we can reduce. So that is how we have taken this project. Of course, application wise is same, and the company should have the furnace and also polymer impregnation facilities they should have, like RTM or a vacuum bagging technique. So any polymer composite, that is one intermediate step, so they should have it. And of course they should also have the binder pyrolysing furnace, and also they should have a liquid silicon infiltration. Application is same. It finds everything. So you all know that the brake disc, from starting from metal to CC, carbon-carbon composite, now the recently, last 4 or 5 years back, the consortium met by the international community, where the Aircraft Brake Disc Manufacturers Association, they declared that CSIC composite is the next generation aircraft brake disc material, like a fourth gen material. So the advantage compared to the CC is very good. Almost all commercial aircraft today is flying with carbon-carbon, no problem. But there is some disadvantages is there, like instability in friction performance, the coefficient of friction, and also the prone to oxidation. Since the matrix is carbon, for some reason the friction dissipating more energy, if it becomes more than 500, 600 degrees centigrade, so the carbon will oxidize. So that is a drawback. Whereas if you replace that carbon matrix by silicon carbide matrix, then you get all lot of advantages, starting from high friction coefficient, stable friction coefficient, high temperature capability because you are a silicon carbide matrix, and so on and so forth. Of course, disadvantage is it is expensive. So this is the Saurus aircraft, our own Saurus aircraft brake disc. Currently it is made up of metallic brakes, copper based alloy with aluminosilicate alloy, kind of an MMC, but they have got their own disadvantage, excessive heating, and also a lot of debris is coming if they apply frequent braking. So that is why we are trying to develop by CSIC by this process. So we have developed the coupon level properties which are in par with the CC composites, which is the Tejas version Mark IV. And you all know that the CMC can be made by these three processes. One is the CVI, I just explained. The second one is you take the polymer. That polymer can be impregnated into the porous preform, and then they can be cured and post-cured, then pyrolyzed, then I will get the carbon. If I take the phenol formaldehyde, I will get the carbon as a matrix. And keep on I do, finally I get the process, I get the product. So this is a PAP process. The third one is that liquid silicon infiltration process, where my starting raw material is, say, for example, carbon-carbon composite, which is porous in nature. And that one will be taken to my LSI treatment, where silicon is kept along with that by calculating the stoichiometric ratio, so that the available carbon will react with the silicon and form a silicon carbide. So thereby I reduce the time. So I use all the three. In my hybrid process, I use first one for interface coating, and the second one is for getting the carbon-carbon porous matrix. Third one is for final process, final composite. So here the first I took the preform, go for the polymer impregnation, pyrolysis, again go for impregnation, pyrolysis, like that I do it for 5-6 times. Then I take it for LSI treatment, and finally my composite is ready. So this is a facility available at NAL, recently established under mission mode program, where this can go up to 1800 degrees centigrade and 1 to 300 millibar is capability. Depending on that, you can play with that. So this facility is used for making this brake disc. So this is the brake disc which you have made. Basically, it is ready for DOD, dynamometer test. So I think my friend Dr. TPD Rajan is there from NIST, Trivandrum. He knows that the qualification is very tough process here. So first we have to go for a disc-on-disc dynamometer test. You have to qualify. Then it has to go for the assembly level test. If the assembly level is a full-fledged brake disc along with the aircraft wheel. Once that is also proved, then we have to go for the taxi trial. So we are in the DOD level right now. Thank you very much for patience hearing. And we are welcoming any partner who can. In the case of CVI, already we have a TOT partner, Azista Composite Private Limited, Hyderabad. So they are ready, almost their ecosystem, they have developed everything. So their 2-meter class CVI facility will be ready first in the country, and they will be start producing the CVI based composites. But for LSI, we are open to, of course, that is also non-exclusive. So any industries who are interested, we are very, very happy to invite. Yeah. Thank you.
Thank you very much for your detailed talk on CMC, sir. Do you have any queries for the speaker? So if there are no questions, we will move on to next talk, the last talk of this session, indigenous carbon fibers by Tarun Kumar Pradi. So thank you very much, sir.
Very good afternoon. I'll be talking about indigenous carbon fibers of CSIR NAL. So, as we are all aware, carbon fiber is a reinforcing material for composites, and it's in form of fiber which is having diameter around 5 to 10 micron. But in this category also, 5 to 5.5 micron is one, and the 7 micron is another one. 7 micron typically is a standard modulus grade carbon fiber, and 5 micron will be intermediate or maybe high modulus grade carbon fiber. And this will have typically 92% or more carbon content, depend upon the grade. It goes up to 96 or even 97% also carbon content in that. We are all aware about this carbon fiber, why it is so popular, because it's having very low density and its specific strength is very high. And the carbon fiber, what I'll be showing is through the polyacrylonitrile route. There are several routes to make the carbon fiber, rayon-based carbon fiber or pitch-based carbon fiber also there. But in aerospace application, pan-based is very popular because it is having a high strength compared to any other carbon fibers. Carbon fiber are used mainly in different form, like the fiber is pulled to itself, what is shown here in the first picture, or it will be made a fabric out of that and made a composite from there, or it may be in form of prepregs, where it will be mixed with some pre-coated resin will be there, or it will be in a choked form, carbon fiber choked, which is again made from the spools only, but very low-end application, this like a tray or something, it can be used, the choked carbon fiber can be used there. And the carbon fiber application, there are various applications. I have listed few. First and the foremost is the aerospace sector, where we all know the primary structure or the secondary structure made of carbon fiber. Carbon fiber composites is there, aircraft, drone, missiles, rockets, all these area carbon fiber is used. Second important sector which is coming up is the transport sector. Very high-end cars, BMW and all that, they are already started using carbon fiber because of its specific strength application. And in metro coaches are also being made from carbon fibers. Third is the energy sector, where the windmill blades are made. Windmill blades normally glass fiber used, but when you have to make a very large capacity or large wing, this glass fiber will not have that. It will have start bending actually. So they will make either in form of hybrid or maybe some the carbon fiber itself they'll use directly for the making of this windmill blades. And also the cylinders to carry the fuels, the type 2, 3, 4, all those also carbon fiber is used in this energy sectors. In the sports sector, golf sticks and various rackets, already we know that. One other interesting application is there, offshore and retrofit. Offshore means for marine applications, where the corrosion is very, very crucial there. And the other metals cannot survive. So carbon fiber composite metal can survive for long. So the one picture is shown that it is for teethers actually, for ships or even for marine platform also the carbon fiber used. Retrofit structures, some of the old bridges or old buildings also can be repaired through this carbon fiber, this one lamination and then with the resin around that. And apart from this, general engineering sectors like pipes, tubes, or structures, and all these kind of things are made from carbon fibers. Here in NAL, this is about the carbon fiber facility at NAL, and we have a facility right from integrated facility, basically starting from its starting material, acrylonitrile polymerization to fiber to carbon fiber. And it is having basically three major processes. One is first one is the acrylonitrile polymer, where the suspension polymerization process is used, and the polymer is produced in a continuous reactor. It's suspension polymerization, and we get a polymer powder from this reactor that will be dissolved and made solution out of that and spun through wet spinning technology. The second picture shows our white color fiber is the precursor fiber, which will be used to make carbon fiber by heat treatment process. The second line, it is a precursor wet spinning line, and third is the heat treatment line, which is starting from 200 degrees centigrade temperature to 1500 degree temperature, is used to convert this precursor fiber to carbon fiber. And the last picture is about the aerial view of the facility. So here, this is a pilot plant facility, which is having like industrial kind of setup only. Your data directly is scalable plant, scalable data we can get from here. And it is equipped with all the related process utilities and process controls. And characterization also done, all the characterization done in-house only in this facility. For the technology, we have standard modulus grade carbon fiber, which I told around 7 micron diameter. And this is equivalent to Torres T300 grade carbon fiber. So this technology was developed, which is having strength about 3.5 GPa to 3240 modulus of tensile modulus, elongation 1.5, around 1.77 around the density is there. And this product was certified through Semilec for 6,000 filament, which is typically used for aerospace application. And the status of this technology is there. Presently, it's not available in India. But yes, we have transferred this technology to one of the government agency for 25 tons per annum production. That is for integrated full plant. And in coming years, this also will be operational. Right now, the civil work is completed and some equipment fabrication work is going on. What we are looking like expected capabilities of industry to absorb this technology. As such, any chemical industry can absorb, but if fiber processing specialization is there, it will be good to absorb this technology because a lot of fibers technology is involved in this one. And what will be the major facility required for production of, this is one just idea to understand what kind of things are required. So we have polymer synthesis, fibers, wet spinning, heat treatment facility, and some process utilities. So roughly about 230 crore. This is from our previous thing. We have got this data. This much capital will be required for 25 tons per annum carbon fiber plant. And potential application already we have shown in first slide where it can be used in various sectors where this can be used. Around 100 ton per annum it is already required in India for static sector. So this is the status of carbon fiber technology. Thank you.
Thank you very much for your detailed presentation on carbon fiber technology at NAL. Do you have any queries for the speaker? Yes. Can you hand over mic there?
Thank you, sir. So is there any readily available supply chain for this particular material?
Readily available?
In the sense, of course, the market currently is looking into indigenous content. So this is an Indian factory.
Yeah. Yeah, these fibers are available in market. It's not like it's not available, but it's not easily available. And there are several grades are there. You may not get the proper grade also in that. So that problems are there in that, even to international market.
No. So as an indigenous industry, is there any way that we can get this in order to improve our percentage? Like
for this product?
Yeah, I mean, fiber is available, but it's not Indian origin.
Yeah.
So
Yeah.
Indian origin from this process, is there any factory already producing?
Yeah, I told that already one technology transferred. So we are expecting another 1 or 2 years this product there, but still it's not sufficient to cater the demand of Indian market. So still a lot of potential is there in that. Around 100 ton what we have got from various sources, so immediate requirement is there. In future when this goes for lower end application, like for some general engineering sector or maybe automobile sector, this demand is going to increase.
So far we don't have option to buy that readily.
Yeah.
Is that the, okay.
So thank you very much, sir. Now we come to end of this session on aerospace material technologies. On behalf of organizers, I thank all speakers for their very insightful lectures on technologies, especially related to aerospace material technologies at NAL. Hope our industry partners have got an idea what NAL technologies are available for commercialization. And also I would like to thank our session reporter, Dr. Prashant Chaudhary, Chief Scientist, SCD, for reporting this session. Now we will break for tea. We'll come back by 3:25, and we have an interesting session on artificial intelligence technologies and at the CSIR setup, which is coordinated by our sister laboratory 4PI. So they will be handling this session. So we will reassemble here by 3:25. So tea is served at just outside of this hall.
Good afternoon, everyone. and welcome to this session on AI-enabled technologies and systems coordinated by CSIR 4PI. We are gathered here to explore the transformative potential of AI across various domains and how it is shaping the future of research and innovation within the CSIR network and beyond. We are privileged to start our session with insights from Dr. Sridevi Jade, Director of CSIR 4PI. As a leading force behind AI initiatives within CSIR, her perspective will set the stage for our discussions today.
Good afternoon to one and all. As the Director of CSIR 4th Paradigm Institute, since it is a session coordinated by CSIR 4PI, in the OW 1 week 1 theme initiative of event of AEISS theme of CSIR NAL. So as per this thing we are supposed to, because since we are a only data science lab of CSIR, we are a horizontal across all themes. So for each 1 week 1 theme event of each theme, we are supposed to conduct some program. So usually since NAL was conducting here, we thought we'll just coordinate one session under this theme as part of our contribution. So that is how we are here today for this. So I think the panel discussion and the presentations are on AI landscape of CSIR. So since the time I joined, I took charge as head of the CSIR 4th Paradigm Institute and now director of the institute. So whatever we did, I thought I'll give a little background about CSIR AI this thing, and in future what we are planning to do. Because since the time I became director of this institute, I have been nominated to represent CSIR in all the AI initiatives of the country. So instead of, basically I was representing DG CSIR in India AI mission, in cyber physical systems, National Mission on Cyber Physical Systems, then National Supercomputing Mission, everything. So I have the whole landscape of how things are going to be in the near future as far as our country is concerned, and so based on that, what should be the landscape of CSIR. See, the whole idea of us being, we are the youngest institute of CSIR and only data science institute is to put CSIR in the data science map of the country. That was the whole initiative. So see, we were a 10-year-old institute, so 2013, and CSIR as such, they have started AI mission, I think in 2016-17, with few projects. Most of them are related to healthcare and cyber physical systems and some instrumentation capabilities. That ended in 2020, and then the phase 2 started in, I think, 2021. So in phase 2, they have been given phase 2. See, both phase 1 and phase 2, the best part was it was always with the industry partner or a stakeholder. The projects were given only who had an industry partner or a stakeholder. So that, once they finish the project, the output or the product, the deliverables of the output is used by the industry or a stakeholder. So that was the condition on which both phase, AI mission phase 1 and phase 2 were operated. In phase 2, now whoever is speaking today, participating in the panel discussion are AI mission phase 2 nodal scientists and project leaders or PIs, co-PIs of the projects. So they will give, because we are planning to, as we plan to cover the AI perspective of the whole of CSIR, we thought the best would be to, the current running AI mission nodal scientists should come and give their views on it. So that was what we had thought, and we got them. So you would be hearing from them on the whatever they are doing in the phase 2, AI phase 2 mission. So this ends in March 2025, and we have already put a CSIR AI initiative proposal called CLAIM. So we thought, that this AI mission is ending March 2024 and CLAIM will take over, but then this got extended to March 2025. So the CLAIM basically stands for CSIR League for AI, of AI in industrial manifestation, basically AI for industry. So this we started, we made a proposal. Again, here also we have the model is that 60% from CSIR, 40% from industry stakeholders, like that. So in this initiative, we have done all the brainstorming sessions, and I think we have around 34 CSIR labs participating in this mission, and we submitted the DPR for this mission, and we are going to now take it forward for the next financial year. So in the meantime, because this exercise we started 1 year back, more than a year back, I think in June 2023. Meanwhile, in March 7th, government cabinet has given India AI mission. I think it was around 10,000 crore to MIT. So that's a huge initiative in which they are going to have a complete AI ecosystem in the country, and there are 7 pillars in that. One is that ethics of AI, then data sets, like that. There are 7 pillars. I don't remember all the 7 pillars. We actually, so I was nominated for that India AI mission for representing CSIR. So I had given a concept note there, and where CSIR fits into these 7 pillars. So I think we fit into the 4 of the 7 pillars. If I am maybe I can read that out. I should be having in my mobile. 1 second, I can read that out, because that would be nice. Then we will know what are, we come under 4 pillars: India AI Compute, India AI Datasets Platform, India AI Application Development Initiative, Safe and Trusted AI. So as our participation in this India AI mission, I had given a concept note. Basically, the concept note was broadly based on the CLAIM proposal we made, but it is slightly different, because we thought this is what we are going to do in future in CSIR, and this should also become part of the India AI mission. See, working so isolatedly and not being part of the government's mission does not make any sense. So basically, we had given this thing saying that we are going to integrate and use AI for industrial applications, because CSIR across all 37 labs, they have a lot of industry participation. So they all have some problems, and across diverse disciplines, starting from nanotechnology to materials to hazard to healthcare, etc. So many this thing. That's how we could get all 34 labs participating. So how do we leverage AI and ML for bettering these industrial applications? So that was the concept on which we proposed for India AI mission. So basically, the objective of this was to have at the end of next 2 years AI-enabled CSIR. So that each lab has AI, because right now there are 10-15 labs which are in the forefront of AI research in the institute and their applications. And also we, as a part of this, we can have at 4Pi, we could develop algorithms. The total data science ecosystem can be set up here, and it can be leveraged to the other labs. So that was the other initiative, and then use it for the industrial applications. So this is what we proposed in India AI mission to do this, and it covering, actually the disciplines it covers is almost matching with the themes of CSIR. So that is what is right now. So we taking this forward in the next year. Basically CSIR AI initiative for industry should be the way forward. And that is how we should go ahead and be part of the India AI mission. That is what I wanted to give a brief opening remarks on this, setting a tone for the talks from the, because they have more knowledge. My core expertise is not in AI ML, whereas the nodal scientists, they have more knowledge. My perspective is from attending, representing CSIR in all the national missions. So from that perspective I spoke, and they will speak from their perspective of AI experts. Thank you so much.
Thank you, ma'am, for enlightening us with the various initiatives of CSIR. Your insights have certainly provided us with a strong foundation for the discussion ahead. I would now like to invite our esteemed panel members and our moderator to the dais. Please join me in welcoming Dr. Sharmishta Palitsagar, Chief Scientist, CSIR NML. She is a Chief Scientist with 28 years of expertise in non-destructive evaluation, sensor development, signal and image processing. Her extensive expertise has significantly contributed in the field of sensor and IoT for process control in the steel industry. I welcome you, ma'am. Dr. G.K. Patra, Chief Scientist, CSIR 4PI. He is a chief scientist with 27 years of experience. He is engaged in research on privacy, security, and safety of concerned vehicles and citizenry services using AI, blockchain, and cryptography. I welcome you, sir. Dr. Debi Prasad Das, Senior Principal Scientist, CSIR IMMT. He is a Senior Principal Scientist and Head of the Process Engineering and Instrumentation Department at CSIR IMMT with 27 years of experience. He specializes in developing advanced electronics and instrumentation techniques for monitoring and control applications, incorporating signal processing and machine learning. I welcome you, sir. Dr. Sumit Saurav, Senior Scientist, CSIR CIRI. His research primarily focuses on developing resource-efficient AI/ML algorithms tailored for societal, commercial, defense, and industrial applications. I welcome you, sir. Dr. Asha Purna Mandi, Principal Scientist, CSIR 4PI. She has an experience of 15 years. Her research primarily involves designing and developing AI-based algorithms and tools to tackle complex problems across various scientific domains. Her fields of interest include privacy security, AI-based solutions for citizenry services, and high-performance computing. I welcome you, ma'am. I now invite Dr. Asha Purna Mandi, the moderator for this session, to take the lead.
Thank you, Rina, and good afternoon, everyone. I welcome all the panelists. So first I will talk about how this session will go on. We will request all our panelists to talk about their work or whatever the AI activities are going on in their lab. And then after that, we will start the discussion round. After discussion round, we will open the floor for the audience. Audience can ask the question. Any industry partner, if they want to know more about our work, so it is welcome. So now I request Dr. I request Dr. Sharmishta to talk about her work on AI and AI-related activities in NML. Good afternoon, and thank you, Asha Purna from 4PI for inviting, though it was a very short notice, but we are here because the subject is a very growing subject now, and especially in context of CSIR, I think we need to have some real great effort to put into this area. I would like to just give a couple of slides on the work, what we are doing with industrial partner, and where I must say AI, but still we are in a very initial stage of AI. It has to go a long way. And thank you, Dr. Sridevi, for being here and briefing us what is the CSIR roadmap towards Indian AI revolution now, I can say. So thank you very much. So maybe I will go there to present. After that, I can take my seat. So I just framed it like AI-enabled technologies. Just two case studies I will show here, where NML, being the metallurgical lab, though we have lots of other prospects too, but being just adjacent to Tata Steel, which is, I can say, our big advantage, just like NAL become the aerospace and at Bangalore. Similarly, NML, just beside Tata Steel, having a couple of advantages. Couple of our technologies we can try at the industry, we can implement at the industry, we can modify, we can remodify, and ultimately we can come to a stage where industry can take up that solution from us, especially Tata Steel. So this is on critical zone prediction of large industrial structure. Though I'll give two case studies, but I'm sure this can be applied to any such structure which are refractory lined. So before going to my own work, actually, this is next-gen manufacturing industry, if I can talk about, and where not everything I'm going to talk, but we know how important each part to make a next-gen manufacturing industry. Each and every item is important. Why I marked sensor and this two part? Because this is the things maybe I'm just going to address. There is big data always associated with that, and that analysis and cloud computing is naturally integral part of it. So, and with that I'm coming to an integrated steel plant, how it is and where, though we have addressed many of the issues, but only two things I am going to show. One is in the blast furnace area, and one is called the pellet plant, which is the pelletization of raw material, and then that can be put to the blast furnace. All of us know the blast furnace is the heart of steel industry. And when we go talk about AI, big data analysis, even for human being or anywhere, the most important part is the sensor. Because you need to collect the data. Our neuron, our brain itself. So if we don't collect the data here, so we cannot do anything. That means the most important part comes the sensor, which is giving us the data. So lots of work is required on sensor, different types of sensor in different applications, whether it is biomedical, whether it is manufacturing industry, whether it is healthcare. So wherever you go, you need lots of sensor, and lots of work is required for the sensor and application-based sensor. Then you need lots of work on the structural analysis of the sensor, where it is going to be used, what type of calibration is required. And when I'm talking about data capture AI, fully automated system, that means sensor has to be embedded on the body. You cannot go and do the work by placing the sensor at that location. Then ultimately it comes to the predictive diagnosis and prognosis, that is the data processing and interpretation. Data mining to segregate false and real data, because when we capture data, there are a large number of data which are false also. That means you need to segregate the data.
Then predicting probability of failure, AI models, IoT, and warning before happening. Or giving information what's going to happen in future. So all these are included here. So now exactly in that way I'm giving you one example here. It's the blowpipe, how it is arranged in the blast furnace. You can see what a complicated structure here. And one blast furnace are having like such 34 blowpipes, and the inside portion is the most important, which is going in. Okay, and that means it is not accessible. You can't access that area that you can place your thermal camera and get the temperature monitoring. And what is the challenge is, the temperature is 1200 degrees centigrade, hot air blows through that. Dimension of the structure, inaccessibility, unpredictable failure. Don't know which blowpipe is going to fail. So here it is very, very important to have this predictive type of model. Each BF, already I have told, and prediction of the correct one prone to failure, that you have to find out. So that they can take a proper action, only that blowpipe can be replaced. And what happens, you can see if it cracks, that 1200 degree air comes out. So what type of threat it is giving? Not only the catastrophic failure, the production stopped, that means economical loss, but there is a casualty can happen. So safety is also a big threat. So this is the adapted methodology we have taken. That means in this case, how we have approached to develop this type of a model. The first thing has been done with the operational parameter. All operational parameter was used to have this CHT model. And from that CHT model, we have generated large number of data for getting the thermal profile. So then thermal profile from that large number of data, then we develop the ANN model. First from this heat transfer model, and if there is a hotspot is here, how the thermal model, that means how temperature is distributed. Like the 320 locations, this thermal spot has been moved, and the thermal profile was generated, and this ANN system developed. With that, what we have done, now you need some sensors to be placed. Then we placed only 4 arrays of sensor. You can see there is 1, 2, 3, 4, like that 4 arrays of sensor with 5. One array was with 5 sensors. And those are the fiber Bragg rating sensors. Here we have used fiber Bragg rating sensors. And then this predictive model was developed. Real-time data was collected continuously from November 2022 to till 23 end. Those real data, the system was again retrained, and after retraining, the error range was coming plus minus 4%. Now the question may come, how will you know that hotspot prediction is correct? That means you need validation point also. So the 2 points was kept as the validation point where the sensor was placed, but it has not been taken in the model for the prediction. So the predictive measured value and the predictive value was continuously we were comparing, and that value came down to plus minus 4 degree. So this has helped now to prevent the onset of the critical condition. We have done for one blowpipe, but that is now if we can continuously give in the 34 blowpipe, and whole data can be captured, and this data can be analyzed, and particular blowpipe can be detected before failure. That is the big work, and that can be our next step of journey. So similarly, this is for a structure which you can see how big. This is again refractory line structure. Actually what happens, these are all refractory line structure. The refractory erode, and when it is eroding, where from it is eroding, nobody knows. So that erosion causes the high temperature at the shell, and that shell temperature we are basically monitoring for giving the predictive model. In this case, you can see most of the area is very visible area, though it is in a height of maybe 20 feet or 50 feet like this, but accessible. Thermal camera can capture. But what happened to the inaccessible area? Nothing can be done. So the industry need was an AI-based thermal profile generation of the burner by embedding very small number of sensor. Because if I put large number of sensor, cost will again go high, so your ROI will be very low, so industry will not take up. So here also we used fiber bracketing. I must appreciate CGCRI here, because all this work, and this is one very good work we are doing with industry collaboration, with CGCRI, and our own indigenous system, everything our indigenous, our sensor, our indigenous CSIR product, our technology is our CSIR product, nothing is marketed other than the fiber, of course. So here we placed, these are the three most prone area for failure. So in those three areas, this 1010 sensor was selected, and you can see in inaccessible area, we have placed 639 plus 11 sensors were placed in the inaccessible area. And with that, now you can see the whole thermal profile generated across the accessible and inaccessible. Here the thermal image helped us to develop the AI model, because in previous case we have the operational parameter. Here we didn't have any operational parameter, they could not give us. So ultimately we have to go based on the thermal image. What we have observed, look, this is backside 21, sensor number 21, and temperature was continuously increasing, has gone up to 700. That means it is continuously giving an alarm which was not detected by the thermography, but this data, when it has shown, what precaution has been taken. Immediately this precaution has been taken, there is a cool airflow arrangement was made, and this is in July 23, I think July 23, and this is in March 24 when they have done the cooling arrangement. Cooling arrangement was done on 2nd of March. So the temperature dropped. That means it has helped that burner, because it was instrumented burner and the whole thermal image was ported in their control room. They could have done this preventive measure, and that's why the temperature dropped and the failure could be prevented. Okay. So what is the present status? We have installed in November 2022. It is still operating, cooling arrangement done, and now based on this, now they want in all 19 burner we have to horizontally deploy. And now if we deploy horizontally, we have to make some phase shift arrangement where you can continuously monitor the data and can give only alarm for the critical point. So then again coming large number of data is increasing in multiples way. Now it is multiples by 20. Maybe this can come to your question. So I actually thought of to giving some what framework is required for accelerating the innovation. So maybe, I think Ashapurna, this can go to your answer sheet when you are asking the question in the panelist, but I can finish it that. AI and Industry 4.0 has moved, being a popular catchphrase to something that is reshaping the way things are making, reshaping our, I think, daily life also. So with that, thank you very much.
Thank you, Dr. Sarmista, for your insightful talk on AI-enabled technology for critical zone prediction and large industry structure. Now I would like to request Dr. G.K. Patra for showcasing our whatever work we are doing in CSIR 4PI.
Yeah, good afternoon, everybody. Yes. So I will basically give a glimpse of the activities that we do in AI, because we are a data science institute, so we do lots of different works on AI. So I'll start with basically the AI profile of CSIR 4PI, the journey that we went across. Though we became a fourth paradigm institute in 2013, the activities in AI actually started quite long back. In fact, my PhD itself in 1997 was in using AI. So I started with that, and then one of our scientists who was doing weather prediction using AI, in fact, he also got Bhatnagar Award for this work. So we started way back in 1996 to 2005, which was an AI initiation. Then later what we do, we went into the AI adaptation mode. The AI adaptation mode is when we actually started learning AI more and more, and then in fact we started looking at something called AI in cryptography, because that was my subject which we were working at that time. So we worked on something called neural cryptography at that time. Then we started working on the domain agnostic AI. The idea of domain agnostic AI is that let us develop tools and techniques which is not specific to a particular domain, but it can be used in multiple domain across various different domains. So that is the way which we started working towards till 2015. In 2016 to 2024, in fact, we started looking at the intervention of AI into various fields. There we talked about agriculture, we talked about security and privacy, and AI into the healthcare. So the security and privacy is something which we worked in this particular project in the first phase of the AI initiative. And then what we are currently looking at is to really look at AI as a disruptive things. We want to look at a sustainable AI, a reliable AI, and explainable AI. So we are trying to move into an era where we can actually, people can believe AI. Right now it is a black box. People don't know how it happened, how the input has gone, how output has gone, but we need to have an explainable things, and that is what we are trying to do it. And it completely aligns with the vision of CSIR at 2030. So the different sectors that we are actually looking at, AI intervention to different sectors, I will touch upon two of them which are part of this particular project. One is the generative AI, where we actually generate synthetic biometric data set, which is where the Aadhaar, UIDAI is our stakeholder. It's basically like that because of the Aadhaar law, the Aadhaar data cannot be given for developing any of the applications and all. Now, to take care of that, what Aadhaar wanted us is to develop a synthetic data set which has characteristics similar to the Aadhaar data set, which can be given to developers to use as a data set and then develop applications, and then Aadhaar can take that applications and run on the data set and provide the services. So that is what is one of the projects that we are currently doing as part of the AI mission project. And the other one is the down one, where you can see these some small ducky town or toy vehicles moving. That is actually a very futuristic project that was part of the AI mission project, where we did the work with Cognizant. Cognizant is the stakeholder. In fact, they funded a project to us, and we delivered what they wanted in that project. Here it is basically for vehicular ad hoc network. The concept is new to India, but I think in Europe and the US, people are already working towards smart implementation of VANET. And we are currently working on the 5G VANET. The typical VANET has a very dedicated communication network, but here what we are looking at 5G as an enabler for communication, because 5G has lots of advantages of implementation, ease of implementation. In any case, we will implement it because that is part of our telecommunication process. So we are working on that, where we basically look into the security and privacy aspects, and we basically use AI for security and privacy enhancements in those things. The other three things what we look at is not part of this AEIS theme, but then they are like kind of one is into the agri theme, where we look at how we look at AI interventions into various agricultural practices which can improve the various agricultural outputs, yields and other things. That there is a mission project which is coordinated by Fourth Paradigm Institute. And the other one is basically to earth sciences. We have a very strong domain expertise in earth sciences. So now we have developed these models. Basically it is developed by Asa as part of her PhD, where she has worked on various developed various AI frameworks for various earth and ocean and atmospheric activities like wind energy predictions, basically on the temperature predictions, all those kind of predictions. How do we use AI into that? The other one is into the healthcare, where in fact we were providing the predictions to Karnataka government, both in terms of number of COVID cases in a weekly basis, so that they can plan for their things. And this was not only that, we started maybe sometime in middle of 21 and started giving till 2023. And we wanted to stop it when everybody felt COVID is gone. No, it is really helping us to plan ourselves. So please continue giving that. So every week we used to give the prediction to them. So healthcare, these are the areas where 4PI is working very strongly. So we started looking at where all we contribute in the sustainable development goals. To our surprise, actually we are contributing almost 9 sustainable development goals, and everywhere, every goal, we are actually looking at AI interventions. Whether it is agriculture, energy sector, whatever you look at, climate modeling, everywhere we are looking at AI as an intervention and working towards that. So this is the AI ecosystem that is available at 4PI, not only for 4PI, it is for the whole of CSIR. We have the mega CSIR centralized cloud storage, which will be made available from next week kind of thing, that people can store their scientific data on all our CSIR can actually store their scientific data onto the mega cloud storage. We have the centralized high performance computing facility where we have the capability to run AI and ML applications. We call it as CHAMP. And then we have, of course, expertise in AI ML thing and domain expertise in earth sciences. And we have other domain expertises across CSIR. So that makes the complete AI ecosystem with tools and other things available for us. So this is my expression of interest. If any industry or any academic institutions or any research institute want to work with us, we are ready to work on physics-based or physics-enabled AI models, because we feel we have a very good strength in understanding physics, at least in the earth sciences domain. And also we will look at explainable AI. That's the future. Without explainability, I think healthcare AI will not be implementable. So we need to have explainability if we want to get AI into the healthcare sector. And then mobility, renewable energy, agrotechnologies, and healthcare, these are the areas where we would like to collaborate if anybody is interested in that. And the kind of techniques that we would look at is like expertise we have is like image analytics, computer vision, blockchain, federated learning, etc. So this is, if anybody would like to collaborate with us, it's mostly welcome. They can contact us. Thank you.
Thank you very much, Dr. Patra, for highlighting 4PI AI activities and 4PI goal towards the AI journey. Now I request Dr. Devi Prasad from CSIR IMMT for highlighting AI on material science and mineral processing.
Good afternoon. As all of you know that CSIR has got about 37 national laboratories all over India. Our lab is named as Institute of Minerals and Materials Technology, where we work with mineral industries. And mineral industries means they convert the ores. The ores may be low grade to the metals which are usable. So there are different processes involved in the mineral processing. In addition to that, there are also some material scientists that develop different type of new materials for different applications, for sensor applications, energy storage application, and all that. So our division is related to instrumentation and process control. So we develop different type of instrumentation for mineral processing, and also we work little bit, we started working little bit for the material scientists for making their life easy by helping them in doing lesser experimentation and generating the experimental data, predicting the futuristic experimental data using AI ML technique. So I have only 2 slides. This is because I wanted not to spend more time on presentation. So in the mineral processing, there are different unit operations, like ball mill, which is used for grinding. So it is a metallic structure, big structure, cylindrical one, and balls are there, and it is used for grinding the ores to finer size. But from outside, you cannot know that what is the fill level of the mill, whether it is half full or full, optimally filled, or it is more than required. So using vibration sensor and using machine learning technique, we can predict the fill level of the mill. We can also predict many other information about inside of the mill, like the condition of the ball, the condition of the material, whether the ball is coated with some moist material so that cushioning effect is there, grinding is not proper. All these are going on in our lab. So some of the publications are mentioned there, so details can be found from there. Then hydrocyclone is another process in which the heavier materials, based on the density and the the heaviness will be separated from the lighter ones by using a cyclonic process, that is a unit operation. But there is a possibility that the hydrocyclone may choke while operation. So once it gets choked, then there will be huge trouble and they have to open and clean the hydrocyclone. So when it started choking, we know that the weight of the hydrocyclone will increase, the mass is increasing. So mass of a body increases means its natural frequency also changes. So from the vibration of the hydrocyclone, we can find out the natural frequency and can predict that the material is started settling, so that corrective measures can be taken. So that is also using some kind of signal processing and machine learning. Then there is an important process where when the ores are ground to finer particles, the finer particles are not suitable for blast furnace. Blast furnace require some lumpy iron ores. So the finer particles are required to be made spherical balls called pellets, and they are made in a pelletization disc. And uniform pellet size distribution is required there. But the process is so complex that all the time the uniformity of the pellet size will not come. Sometimes they will be undersized, sometimes they will be oversized. Undersized and oversized are actually rejects, and they will come again back to the disc for again making pellets. So how presently it is happening, there are human supervisors who are moving in a dusty atmosphere 24/7 in a noisy and dusty area, and they are watching the particular disk area and actually controlling the pellet size. So we used an image processing technique where the same analysis what the brain is doing of a particular human supervisor can be replaced by image processing method. And we also used deep learning there for classification of the size, and those are also published in three journals in different type of analysis were there. Then there is a thermal arc plasma where high temperature is maintained about 10,000 degrees centigrade, where the melting and reactions are going on. There also monitoring is a difficult task. So some kind of gas is there, reactive gas or inert gas is given, and also very high temperature, glow is very high. So there are a lot of things to be monitored, like cathode position, the parameter inside the particular plasma. So those are also, what we did is we did systematic experiments with lot of sensors, the data coming to the computer, then we match the pattern of the data with the process parameters. So that is also, this can be available in this particular journals. So recently we are working on, now the ores will not be transported from the mine area to the industry by trucks and trains. Now attempts are going on that they will be transported through slurry pipelines. So ores will be ground to finer particles, and then it will be mixed with water, and they will be pumped in the pipeline so that environment can be saved, the roads can be saved. So there is a possibility that while moving the pipes may choke because the material may settle down. From outside, can you predict that my choking is happening or settling, material settling is happening? So we are also working on this. Next. So for material science, there is a group working on electrochemical method for energy storage devices. So for electrochemical material development, there is a cyclic voltammetry experiment is done using electrochemical workstations. So with different scan rates, they generate this particular plot. So to generate that plot, they take a lot of time. So they gave us 4 or 5 cyclic voltammetric plot for different scan rates. Then we fit it using a multi-layer artificial neural network. Then we generated all other possibilities, all other possible cyclic voltammetric plots. So using those cyclic voltammetric plot, they found the performance of the material, and then they designed the material. So that is also published in a very good journal, Chemical Engineering Journal, which is having a very good impact factor. Similarly, they develop a supercapacitor which is having an electrochromic electrode. Electrochromic means when the charge is stored, then the color of the electrode changes. So by seeing the color, you can know what is the amount of voltage stored there. So a human being can see, but can we see it using a optical sensor so that sensor can tell what is the voltage? So at different colors, we did a neural network fitting with different voltage, and that also helped in publishing in a good journal called SMAL. There are two technologies already commercialized, which is used in JSW pellet plant 1. That image processing based online pellet size monitoring that human was monitoring. Now we made a camera based image processing technique, so that we named it as eye on pellet. Then after analysis, we also made a control system by which the corrective control actions like feed rate change and the RPM change, RPM of the disc change happened online with a complete integration with the plant DCS system. So this is one we named as Expert Eye on Pellet. So this is all about some of the works, but there is unlimited scope in industries. Wherever there is a human interventions, wherever you require multiple times, you take the sample to the lab and check, or without an expert knowledge, it is not possible. Then there is a possibility of converting it to a AI/ML based system, monitoring system, and also control system. So if any industry is having any system where you are fully dependent on expert advice or expert supervision, then there either camera or any other sensor, or some sensors are already there, like current sensor, voltage sensor. From there also information can be retrieved and control action can be taken. Thank you very much.
Thank you, Dr. Devi Prasad, for your informative talk. Now I request Dr. Sumit from Siri for presenting AI-related activities in Siri.
Hello. Yeah, very good evening to everyone, and I would like to thank the organizer for inviting us here to give to introduce AI-related works which we are doing in our lab. So I am from CSIR CD Pilani. So we are actually at a very remote place in Pilani. It's not very well connected to cities, just like ma'am told about Jamshedpur, Bangalore. So we are in sort of a town. So industrial interaction is very limited. So as my ma'am mentioned that CSIR has been executing AI mission mode project. So we CD has been the coordinating lab for the both two missions. So during the first phase of the AI mission, we actually sort of established an AI computing facility, that is 5 petaflops GPU facility for AI deep learning training. So these are basically NVIDIA DGX systems, and recently we upgraded it to, we also upgraded an inferencing cluster, that is P40 GPUs. So we have a cluster of GPUs for AI ML model training as well as for inferencing, and there is 100 TB storage facilities also there. So this facility is being used by our different CSIR laboratories, sister laboratories, for training and testing of the DL algorithms which were proposed during the AI mission. And the facility is also available for universities, industries, who wants, they can use the facility on charge basis. So during the last two phases, we propose several activities related to AI. But here I will be discussing only few of them because of time constraint. So the first activity actually was related to industrial action recognition. So we know visual computing is one of the key technology for Industry 4.0. And for such action recognition is in Industry 4.0 is very crucial because it helps to, monitor the sequence of actions and keep tracks of time for each action. Also, it can help to record the time for a task, and it can help to analyze the learning index. So we created, since there were no data set available for such tasks in the literature, we collected our own data set. This was actually the data set of operator operating a lathe machine. So there were we collected total 3,428 video clips of nearly 10 actions. So we know that during operating a lathe, there are lots of smaller actions. So we try to label those data and train AI model, and we achieved accuracy of 94.72, and we implemented the trained model on a small computing device, small resource constraint embedded platform. So this is low cost because ultimately to be useful in any industrial application, the algorithm has to go into smaller edge devices. Then only it could be useful. So this is some of the demonstration that person is handling. And we also worked on detecting anomalies, whether the person is executing their steps properly or not. Because if the sequence of his steps are not executed properly, then the item on which the person is working will not meet the requirements. So we work on both action recognition as well as anomaly detection during performing any task. Next, we also further improved the architecture and included human-object interaction. Like we should know which tool the person is working on. So this could be, earlier we worked from only lathe machine, but this could be applicable for other tools also. The other project which we are working on is human drowsiness detection system. This was for drivers and industrial workers. So as we know, one of our sister lab, CRRI, conducted a survey in which they found that 40% of road accidents are due to doze off at the wheels on 300-kilometer Agra-Lucknow expressway. So this project actually aims to address the issue related to monitoring and detection of drowsy driver behavior, and we used physiological as well as physiological as well as behavior methods. So behavior methods includes monitoring driver facial features, and physiological methods monitors the driver ECG signal that was attached to the steering wheel. So here ECG sensor was there, so that used to capture the ECG signal, estimate the heart rate of the driver during normal and drowsy state, as well as there was camera that used to capture the behavioral measures using eye blink, yawn, eye state and all. So we designed our own architecture for eye state detection, whether the eye of the driver is open or closed, then mouth yawn detection and blink detection. And these algorithms were again implemented on, this is Intel OpenVINO tool. This is just a 10K device. It is used with Pi board and a camera. So this is the demo. So we experimented with the simulator, but now we are collecting we are testing the system in real environment by installing it on a driver, taxi and buses in Bangalore-Chennai expressway. And also we are collecting this was collected using simulator, now we are collecting real world data. Finally, we also worked on power line infrastructure monitoring, where we aim to detect different power line components and identify faults, any faults or anomalies if present in that. So this project was done with NL, CSIR NL. So they decided the SOP and help in collecting the data set, power line data set across from different power line companies across the country. And our task was to develop deep learning algorithms to detect different components and analyze faults in that. So this is pretty monitoring power line infrastructure is very essential to prevent complete blackout, and that leads to lots of losses to industries. So we thought of using the power of UAVs as well as AI to regularly monitor the power line infrastructure, and so that we could do the predictive maintenance and to prevent those blackouts and losses to the industries. So this is some of the, we designed algorithm, trained and tested it on the data set, our own data set. So this is our own data, and these are some of the results which we got. And we on the data set, we actually got something like a test accuracy of more than 90%. So that is pretty good, given the challenges, because the images were taken under different conditions where there is sunlight, cloudy, during different daytime, evenings, sort of. Yeah, so this was all from my side. So actually we were working on a couple of projects, but I thought to just, due to time limitation, to give some introduction of only few of them. Thanks.
Thank you very much, Dr. Sumit, for highlighting AI-related activities in CD. So we are running short of time. So I may ask maybe 4 questions to 4 panelists, and we'll open the floor for, or? Okay, then okay. So we can open the floor for audience question. Okay, so my first question to Dr. Devi Prasad. So how is CSR facilitating in adaptation and integration of AI technologies within industry in India?
Yeah, thank you for the question. First of all, the advantage of CSR is a multidisciplinary organization. Starting from leather to ceramic to minerals to medicinal plants, all domain we have expertise, and each and every labs having some computer scientists, AI experts, and on the above we have 4 PI having complete expertise on data science. There are labs like Siri Pilani having a lot of expertise in electronics. Therefore, any type of problem to be solved in AI is artificial intelligence. Like human is having some kind of intelligence. There are some intelligent persons, there are some persons who are not so intelligent. There are employees who are very intelligent, there are employees who are not so intelligent. But all organizations, they require intelligent people for their work to be done. Similarly, since we have a lot of domain expertise, and facilities are there. So any kind of challenging problem can be converted to a AI-based solution. That can be only a software where the data is already there with you, and our people can actually take those data and analyze and give you some solution. Or if it is data is not there, our people can actually integrate sensors and collect their own data, and then also give some kind of instrumentation solution, like Madam is contributing to Tata Steels for their own problem. There may be somewhere periodic maintenance is required in an industry. New kind of automobiles, new kind of industries, new kind of production facilities, Industry 4.0, 5.0, where machine learning, without machine learning, they cannot be possible. Therefore, CSIR has got full expertise because they are mostly experimentalists. Unlike other academic institutions, we do a lot of experiments to validate the problem. Therefore, CSIR is the best place where the AI-based systems and solutions can be developed for the country.
Thank you, Dr. Devi Prasad, for your answer. Now, my next question is to Dr. Sharmistha. What role do public-private partnership play in accelerating AI research and its practical deployment in industry?
Thank you, Ashapurna. Before going to answering your question, I am just taking liberty to take another part of one part. See, in the CSIR AI mission, I personally feel when I was associated with even the meeting of CLAIM, the next program was going on. 37 labs with expertise in different areas, various areas. And each lab, if we are involved in doing AI, the result will be a very, I can say, incremental, delta incremental. Instead, if we can have, just when I am coming here and seeing that 4PI, Siri, the facilities they have developed for carrying out the AI work, because many of the lab are not having this cloud computing facilities where we can store large number of data and can do the analysis. So this, now the time, maybe it is very, very important to join together, because I am facing the same problem being at NML. We do as per our capabilities, what is available. And if every lab thinks I will have an 100 TV facility, then CSIR has to invent lots of money to equip every lab into that level. So I request ma'am, actually this I raised for you only. I request ma'am, whatever we are talking in the CLAIM, which is our main objective, we should have a team of AI expert who will help the other all labs for their own problems to come up to the implementation stage where like when we talk about AI now, we talk about NVIDIA. We talk about any other institute, but why not CSIR with their own capability can come up with those solutions when tomorrow we can hear, yes, CSIR is there, go there and we will have the AI solutions. Team is required where 4PI and Siri can take really the lead, ma'am. So this is my personal request for this. So coming to your industry public interest, so as you have seen that most of our work, Siri also is doing, everybody is trying. When you start work, many times we start work as a hobby work. That means we take a project, we do the work and then we go to the industry. But I feel the industry, academic and the sector, public or industry sector should join hand to get the problem from the beginning. Because at least at the end it should go to the real-time data. And if we don't have the real-time data and our system is not equipped with the real-time data, then ultimately the whole effort will go in vain. Because your data is not going to solve, not going to predict the actual solution, not going to give the actual solution. So this industry, academia, CSIR lab, that is the laboratory, should join hand from the beginning, and sponsorship can get from all, problem can come from all, and meanwhile we can develop our own expertise in AI in such a way that any of the problems we can take up with a high confidence level. That's all from me.
Thank you very much for your view. When we design and develop the AI-based solution and it is a deployable solution, then we need to think about like security concern. The solution should be trustworthy, transparent. So in this direction, I would like to ask Dr. Patra, what CSIR is addressing the ethical consideration in AI research and development.
Yeah, when it comes to healthcare, these ethical concerns come first because you cannot give the privacy of any person when you are collecting. So we have this project on cohort where we collect lots of data. I think NL also did collect lots of data. And there was a major concern, many people didn't give the blood sample saying that no, why should my parameters be known to somebody else? So that's something which was a concern. So looking at that, in fact, the cohort project was designed in a way that they will follow the HIPAA guidelines. The HIPAA guidelines is a US-based guidelines to handle data in an ethical manner. Now, each lab as such is supposed to have, any lab which is collecting data is supposed to have an ethical committee which needs to actually approve that yes, ethically these data can be used. Before doing the data in an ethical manner, there are lots of pre-processing needs to be done. Maybe an anonymization or something needs to be done and provided it. Now, like lab like IGIB and all are into it, they are doing it. Few labs like us, we are yet to create an ethical committee because we are not generating healthcare data, but then certainly we generate lots of different data. We should also look at ethical committees, or at least use the facility of other labs who has the ethical committees to use that. So ethical concerns are there. The other thing is privacy concerns. Privacy concerns are, we actually were not bothered about privacy a few years back. All of a sudden, when it started, people talked in the US and all about privacy. We also become kind of alive. Okay, no, we should also worry about privacy. Otherwise, everywhere we were giving our thumb impression, we were giving all information, we never bothered about it. Now we are bothered about it. We are looking at, India is coming out with this DPDP Act has already come, but then the rules haven't come yet. The Data Privacy and Data Protection Act. The rules, once it comes, we will also follow these things in a manner that our privacies are preserved, in a sense. The concern that we have is when we talk about security and privacy don't go together. So the moment you increase the security, your privacy goes, and if you increase the privacy, your security goes. So I put it like a Heisenberg's uncertainty principle, where like you touch one, you lose the other one. But we need to find out a middle path where both privacy and security are handled, because both have its own importance. So we are working towards that. We will see if in future we should have techniques or technologies where both privacy and security are handled in a simultaneous manner. Thank you.
Okay, thank you very much. Now my next question to Dr. Sumit. See, for skill development, capacity and capability building for AI skill, what is the CSI strategy? What do you feel? Another way you can see that how can the industry and CSI work together to bridge the AI gap, AI skill gap?
Right now we have the Jigyasa programs, right? So where we are getting students from different colleges every time, and some regular interval. And in our institute, we used to provide those trainings, right? If students are BTech, then we start with the scratch, something 1 week rigorous training. Secondly, we do hire interns, right, from different universities, private, government universities. They do a 6-month thesis or 1-year thesis. So they do work with us on different live projects, some portion of those projects. Finally, we are very lucky that we have ACSIR, right, our academic partner of CSIR, and we get lots of IDDP PhD students from them, and they from starting itself from if they are IDDP from second year itself they get involved in the projects, right, whatever the projects, AI related projects we are doing, and PhD students, of course, they stay with us for longer duration, and they work on these AI-related projects. Finally, I just want to say that, right now, these students doesn't get industrial exposure. So actually, they need to have such exposure. They are in R&D lifestyle, but they don't know about industrial lifestyle, how they are. So I think in ACSIR itself, there should be provision of 6 months, industrial experience to those students during PhD itself. Right, so that could be very beneficial for us also, and for students also, because that will prepare them better compared to whatever is happening now. Yeah, thanks.
Okay, thank you very much. My last question: what is the future direction of AI in CSIR? It is open to any of the panelists who wants to take a call. I think in the opening remarks already, Dr. Future direction of AI in CSIR.
That I actually said in my opening remarks. So, and also the concluding remarks maybe. See, I can also say, the whole, what Sharmista said, see that project when it was envisaged that all labs should participate. It's because we wanted an AI-enabled CSIR. So we did not decide that this is the lead lab. Only thing is, we said that we will give the AI ecosystem, we'll provide it at centralized one at CSIR 4th Paradigm Institute. That was what we said, and we handhold also. And we see the future would be like we should be part of the India AI mission. We shouldn't work in isolation. And most of our, all our AI, see there is some research involved in developing tools, algorithms, that and all we will do at 4th Paradigm Institute. But the rest of the lab should get us the industry applications. So that, with that in mind only we propose that, and that I see as the ecosystem. Anyway, we are in the process of having it. Only thing is that algorithm, that also now we started at 4th Paradigm Institute. And Siri had a very good, because they were coordinating the phase 1, phase 2. So they also have a very good niche expertise in AI. So I think they should also be taking initiative. But eventually we should be part of India AI mission. That should be our way forward. But I can leave it to the audience to say whatever they have.
If there is any question, then we can take from audience. Otherwise, I would like to conclude the session. Is there any question? Okay, thank you very much. Anyway, thank you.
Now I request Dr. Manabendra to conduct a final session of the day. Over to Manabendra.
Good evening, everybody. I think last but not the least, we have a very important session now, session 5, that is on indigenous development of technologies for advanced devices and laboratory instruments. We have two very distinguished speakers with us from our sister CSIR labs. The first talk will be by Dr. Asha S.K. She is Chief Scientist and Chair, Polymer Science and Engineering Division, as well as Professor ACSIR. Her areas of research are polymer science, chemistry, solar energy research, material science chemistry, including nanomaterials, additive manufacturing of hybrid materials. The second talk will be by Dr. TPD Rajan sir. He is a Senior Principal Scientist in NIST. He's primarily focusing on composite materials, functional graded materials, nanomaterials, light alloy surface engineering, centrifugal casting, and advanced material processing. So with this brief introduction, we request Asha ma'am to please enlighten us with her talk.
Okay, good evening all of you. Yeah, so this is a fag end of the day. All of you are maybe waiting for the session to end. So let me first thank you for having me here to introduce the project on aramids at NCL and BITRA. So, so what are aramids? So aramids are aromatic amides, which are synthetic fibers having a rigid structure which has very good tensile strength and thermal properties. There are two classes of aramids, that is the para and the meta aramids. So this is the para aramid, and this one is the meta aramid. So the para aramids, they have the benzene and the amide bonds in a 1,4 connection, which gives it a rigid structure. So that gives its high thermal strength and tensile properties. It is as strong as steel. Whereas the meta, the difference is that the connection is 1,3 linkage, so it is a kinked structure. So it does not have as much strength as the para ones. So these materials, these are, as you can see, they because of the high properties, especially the para one, this goes for, this can go as bulletproof applications. This can absorb and dissipate impact. So they go for bulletproof applications. And because of its lightweight nature and also its high thermal property, high tensile properties, it goes in the aerospace applications also. On the other hand, the Meta, they go for this fire retardant applications. And there are a couple of countries only where this is developed. Historically, the aramids was first introduced by DuPont in the early 1970s. Then the Netherlands, AkzoNobel, and now then Japan, France, and China. These are the only countries that develop these materials. And in India, in India, actually, we are one among the top 3 importers of this material. Globally, this you can see the this graph that shows the market value of these aramids. So in 2024, about 4.3 billion US dollars is spent for this aramids. And this is expected to grow at a CAGR of 8% till the early 2030s. And in India, the finance is about of the order of, it is growing at a rate of 10 CAGR, and we are importing the entire thing. We do not produce this in India at all. So it involves the lab scale synthesis of the material, then the fiber spinning, and then the scale up and applications. So actually, our visit here to NAL has been very fruitful. We saw this carbon facilities today, and we came to know that about 20-25 years back, NAL also had developed this process for para-aramids. And some technology transfer also had happened. But maybe our country was not ready at that time to take it forward. Now, especially with the government's initiative to make in India projects, especially in the technical textiles, like the carbon fiber, the Kevlar aramids. So there is government initiative, especially the textile ministry has this NDTM, that is the National Technical Textile Mission, whereby they want India to develop these materials indigenously. So they have, NDTM has been sanctioning projects to various labs who can develop these fibers, indigenously in the lab. So last year, NCL and BITRA, that is the Bombay Textile Research Association, together we were sanctioned a project for developing this para and the meta aramids. So the deliverables in this are, this is the scheme for the para-aramids. This is the diamine and the diacid chloride react to give this amide, polyamide. And so the deliverables for this project are to develop or demonstrate scalability at 1 kg level and of spinnable aramids. So in this slide and the next slide, we say that we show what our progress has been in this area in the last 1 year. NCL develops these polymers, and BITRA will do the spinning. And each step is filled with a lot of challenges, especially this being a rigid aromatic structure that does not dissolve in any material, any solvent. And so the process, polymerization, is also a challenge at each scale. So currently, after 1 year of rigorous work, we are at a scale where we can, in the lab, we can produce at 50 gram scale of the required viscosity. And especially this rigid rod polymer, what happens that for spinning, it needs to have some particular concentration. So if you increase the concentration, viscosity increases and spinning becomes difficult. But fortunately, in this case, these materials are rigid rod and they align to form what is called the lyotropic phase, means it is a liquid crystalline phase. In that phase, even when you increase the concentration, once it starts aligning, the viscosity drops. So that phase can be used for spinning. So what is shown here is a birefringence when you observe this polymer in sulfuric acid under the microscope, which means that, what does it say? It says that the polymer that we have developed at NCL is of the right molecular weight, high molecular weight. So it is aligning to form this lyotropic phase. So these are the characterizations that we have done, and we are comparing with the literature data and to show that the product or the polymer formed is of the structure and the properties that is reported. So in the last 1 year, during the last 1 year, we have been able to develop the polymer, and one successful first attempt at spinning also has been demonstrated at BITRA. So the next challenge after the polymer synthesis is the spinning. This is an infusible polymer. It does not melt, so melt spinning is not possible. It has to be done in solution state. And as I mentioned, since it does not dissolve in normal organic solvents, this is dissolved in sulfuric acid, that too concentrated sulfuric acid and oleum. So the facilities that handle it also has to be that grade which can handle sulfuric acid, like Hastelloy or steel of particular grade. So here this is our first or one or two attempts where we could dissolve the polymer in that concentration. So at this concentration now this is like 19 weight percentage, which means it is formed the lyotropic phase, which means like these are like rods going down a stream which are aligned in one direction. So then it helps dissolve and then form a fiber. So this is the spinning setup that Bitra has developed. And they were able to show the first proof of concept of spinning. A lot of optimization is remaining there. We saw the carbon facility here and we realized what are the challenges that we have to undergo to get the spinnable grade. But we have a couple of more years, and we will also try to contact the original scientists here who worked on this so that we don't reinvent the wheel. We try to gain speed because there are industries also associated with this project, because that was the mandate of the NDTM, that from the beginning industry has to be there, who are willing to take it up once we demonstrated 1 kg level, then taking it forward. That is what, I mean, there are a couple of industries. So yeah, this is a couple of 4 slides that I had to present to you today. Thank you.
So we thank you, ma'am, for, I think both of us are getting these static shocks. So yeah, so the floor is open for questions.
So between 10 to 20 weight percentage only the polymer will form lyotropic phase. That too if the polymer is of the high molecular weight. So in that concentration, because if you keep increasing the molecular weight, viscosity keeps building up. But once it reaches the 10 weight percentage and when it starts aligning, actually viscosity drops. So that helps in spinning.
What are you targeting to make? And then, for example, you said you have seen NL's carbon fiber facility. So we intend to make them into preforms and then composite structures. Likewise, what are the forms in which you would like to convert these finally for application?
So the project target as of now is to develop it into fibers, not into fabric. At that fiber level, there are the industries, I mean, there are several industries which are willing to take it up at the fiber level. The applications are several. Like earlier it used to be mostly in the defense application. Now more civilian applications are also coming. That is why the demand is increasing. So I hope that once the fiber is available, so fabric and other applications also will be there.
If there are no questions, we'll thank ma'am for a very nice presentation. We invite our next, last but not the least, Rajan sir, and he will be delivering the talk on lightweight alloys.
Good evening to all. I am extremely grateful to NIL for giving the opportunity to present this talk on lightweight alloys and composites for aerospace applications. In the area of lightweight materials, we are working on mostly on aluminum and magnesium alloys, metal matrix composites and functionally graded materials, casting simulation, especially for the solidification processing of different castings used for varieties of sectors. The near net shape manufacturing process, that is to create components based on the materials being developed. And near net shape process includes fuse casting, then liquid metal infiltration process and so on. And we also do surface engineering to improve the corrosion properties of the components which we develop, normally the prototype components. And we also develop mostly on the product development. So that means if a user comes and tells that, okay, we want this product of this particular specification or the materials properties. So first our duty is to develop the alloys, mostly lightweight alloys, then convert it into the product. That's what normally. And few products which is mentioned here mainly are focusing to automotive, aerospace, defense, foundry, energy and biomedical sector. And to start with, the first one is an engine mounting frame. It's an aluminum 356 alloy, which is aluminum 7 silicon 0.35 magnesium and with a few other alloying additions. And this is mainly, earlier it is being imported from the French. Then we have been given the duty of indigenization and we have done few components, and one such component is the engine mounting frame for the GSLV programs. Then we also work with the other strategic organizations just like CVRD for the development of aluminum alloy pistons. And this is again an aluminum silicon copper alloy which is being developed and which requires high wear resistance and high temperature properties. And we had supplied to CVRD, that is DRDO organization Chennai, that's for mainly battle tanks. And here the process is used is fuse casting, which is a near net shape process, and the high silicon alloy with the copper and the nickel additions, because nickel gives a high temperature phase which is stable and which is being used. And the third one is the mounting bracket for Hindustan Aeronautics Limited Foundry and Forge, which is developed by magnesium. And low pressure casting is mainly used to make components with porous free castings, because normally if it's a gravity casting there is a lot of leading or the sand castings issue is there. But when we use low pressure casting, the casting problems can be solved and we can get a better premium quality casting. This is an engine, the mounting bracket which is developed for HAL. Then another component area which we had been working for many years is on casting simulation software jointly with IIT Bombay, and we have developed this virtual casting and AutoCast Plus, and this AutoCast Plus is already in market and more than 200 plus licenses have been given to various industries and academic institutions. Industries, they mainly use it for simulation of their castings, because before going for the actual castings, the runner, riser design, the casting shrinkage control, porosity control will be done using the simulation software, and then finally they will design the mold before making the castings. And the other end, we can see the aluminum SIC first gear housings, again for the lightweight compact battle tanks. And it is for, again, CVRD. And the main requirement here is high wear resistance with high stiffness. So incorporation of silicon carbide particle into aluminum, we are able to make this first gear housings. And other a couple of products are with automotive industries, especially the aluminum crankcase and aluminum FGM cylinder liner. In the case of aluminum crankcase, earlier they had been using this cast iron systems, so which is having heavier weight. So to reduce the weight of these things, we had gone for this introduction of aluminum silicon alloys. And this aluminum functionally graded cylinder liners are being imported from Germany, and our duty was to make a high wear resistant cylinder liners. And here what we had used is, we had used the centrifugal casting technique, which has a high silicon alloy, which is a A390 alloy having higher silicon. When we centrifugally cast it, the density of silicon is less, and so it goes to the interior periphery, and thus the tribological properties and strength can be improved, mostly the tribological requirements, because when the piston is moving in the core of the cylinder liner, the wear and has to be less, and the temperature which is being generated has to be dissipated quickly. That's a functionally graded component. And the last component which you can see is an aluminum functionally brake rotor disc, which is again aluminum SIC systems. Here again, this is also made by centrifugal casting, where the presence of silicon carbide, which has a higher density than silicon, which has a lower density than that of, that is around 2.5, which goes to the interior periphery in the case of cylinder liner. But in the case of functionally graded brake disc, in the case of functionally graded brake disc, brake disc, the particles goes to the outer periphery because of the higher density, 3.2 gram per cc. So these are some of the components which are developed for both aerospace, automotive, and defense systems. To elaborate on the aluminum alloy components developed jointly with ISRO, especially with VSSC and Liquid Propulsion Systems Center. So we made various components starting with battery boxes for INSAT series, mainly the lightweight requirement. Then elbow joints for PSLV, mainly this fuel tanks, liquid propulsion engine uses these inlet pipes. And these mounting frames for GSLV, the bottom three U bracket interface frame and the engine mounting frames are fixed, and we can see in the right top corner of the, which is used for GSLV programs. And currently most of the, what our duty is to develop the product with strategic specification properties, then transfer it to the document to ISRO, and ISRO will either give to a company, and most of the components are being developed by our Hindustan Foundry and Forge division, and some has been given to other companies. So currently which has been used for the product. Because one of the problem is these components are having very minimum order quantity, so we cannot have a more number of pieces and also selective, but the properties are very stringent for the premium quality castings. So we also have this liquid low pressure casting techniques for magnesium alloys. Again, magnesium alloys are further lightweight when compared to that of aluminium. Here we, as I had mentioned, the first component is a helicopter component for the HAL. And the bottom we can see there are a lot of automotive components which are developed with using low pressure casting. There is AZ91 aluminium zinc alloys for triple clamp. Then LM25 low pressure cast alloys for compressor cover, differential cover, and oil strainers mostly for automotive sectors. And we also work large part on this metal matrix composites and functionally graded materials. So MMCs are mostly the aluminum composite systems or any metallic composite system with the introduction of either silicon carbide or boron carbide or graphite or any particles improve the properties. And we also had been working on the functionally graded systems where in a particular region of the component will have a improvement in the properties. That is, we have a specific property requirement in a particular region, so we fabricate those things. And we had been working on this aluminum graphite for automobiles, connecting rods, functionally graded cylinder liners, and all those other components I had shown. And we also work on this lightweight 212 for aluminum SiC armor plates, again jointly with CVRD. Well, let's go into the fundamentals of this one. So a couple of components I will show. So these are some of the lightweight aluminum alloy components which is developed or used by Vikram Sarabhai Space Center, and we are also part of few of the components where we have done the fundamental work for the prototype component development. Again, this is most of the lightweight titanium components which is used by the VSSC, but we are not much working on this area. And I have some. We also work on this neutron shielding materials with BARC, but here the requirement is that the boron carbide particles have the neutron shielding capacity. So we incorporate this particle in the aluminum matrix, and these are being made to panels. And these panels are used as a containers for transporting the spent fuel from the nuclear reactors to the other sites, dumping sites or preserving sites and so on. So there we develop some of the materials and supply to BARC. So another process which we are working is on liquid metal infiltration process. Here what we do is we make a porous ceramic preform, and this ceramic preform is placed in a preheated die, in a hydraulic press, and then this preheated die, the metal aluminum alloy or the required alloy is melted in a separate furnace, then it is poured to the die, and then it is infiltrated through the porous region of this preform, and the composite is made. And this particular process is used to make the thermal management plate for our light combat aircraft. And And we also have a pilot scale excuse casting facility at CSIR NIST, so which is of a capacity of 340 tons and the melt capacity of 100 kg, and a casting weight we can do is 1 to 5 kg, and a product size of 800 by 800 we can make, and thickness of 1.5. And this we are collaborating with many industries, and this particular scroll compressor component is jointly developed with Atlas Copco, which is a Belgian company, and we had supplied this product to them. And because here the requirement is high wear resistance and high thermal conductivity. So based on the property requirement, we choose the alloy, we develop the alloy first, the optimization is done, and then finally we will go for. Now we are working with other compressor heads and other components with the WABCO and other industries. The currently program is on. So this is what I told, that's a porous preform where we can see that, and once you apply, pour the metal and squeeze infiltrate, we will get a composite like this. So here we can see this is almost a high volume fraction of silicon carbide particles infiltrated with liquid aluminum metal. So this concept can be used to make thermal management plates, and thermal management plates requires low CT and high thermal conductivity. Normally we know that aluminum alloys have very good thermal conductivity, and then we have even copper has better one, but the problem is the CT of these alloys are very high. So we have, for any electronic component, the CT has to be below 10 ppm per degree C or per Kelvin. So we had used to make this concept. So here what we had used is an aluminum SiC with aluminum silicon magnesium modified alloy and silicon carbide particles of green variety, because we have two varieties of silicon carbide particles. The electronic grade green variety is used, and 50 volume fraction of the particles is initially used, and 50 micrometers average particle size and 68 volume fraction, and we are able to achieve a density of 2.9 and 186 BHN of hardness in as cast and 210 in heated conditions, and CTE of 9.73 and the thermal conductivity of 176. And varying the volume fraction of SiC, we can tailor even up to 210 watts per meter Kelvin we had done. And the compressive strength of 491 and a modulus of 119 MBA we had achieved. And this particular composite material is used to make the thermal management plate. That is, this particular plate is being currently imported by the AD Aeronautical Development System, and it is being fabricated. And this plate is used in the digital flight control computers of our LCA. And this is also find application in other systems also, even the unmanned air vehicles and so on. And here normally this have the PCBs, printed circuit boards, which controls are the whole flight systems, and 4 PCBs are there, which both the sides of this one we mount the PCBs on this thermal management plates. The requirement of this one is mainly to conduct the heat and dissipate it, and each flight has this DFCC, and 4 plates are being used, and the properties achieved are, the target properties are less than 3.01 gram per cc, thermal conductivity of greater than 150 degrees watts per meter Kelvin, and the coefficient of thermal expansion is 5 to 10 ppm per degree C, and X modulus of greater than 80 GPa. And this is the imported one, and this is the indigenous one, and we had transferred this products, almost 20 products to ADE, and now ADE in turn has given to their fabricator, that is Bharat Electronics Limited in Bangalore, and they are going to put the first component. So initially what they are doing there, instead of completely replacing 4, they will put 1 of our indigenous one and 3 of the Indian one. And parallelly now we are going for the airworthiness certification with the Semilac, and after that the real product will be put in use. And initially we will be making these components in NIST Trivandrum, and then finally either we will hand over to the HAL or to any of the other industries. So this is what I want to just share it. But I have other products also, which want of time will not go in details. Thank you very much.
Thank you, sir, for a very nice talk, and the floor is open for questions.
Yes. Yeah, vacuum. Yeah. Yeah, in my because we can use vacuum also for infiltration, but in my study I had used SCUS infiltration. That is, we use the hydraulic press ramming, preheated ram, pour the metal and apply the pressure, and the pressure is around 75 megapascal. So vacuum is also possible, but we have not used in a particular case vacuum. Silicon carbide currently we are getting from CUMI, Carbon Universal. So even they are not manufacturing this electronic grade. They are even importing the larger particles from Russia, and then they are powdering it and grading it and supplying to us. Special for?
I mean, why this particular panel so special that we want to replace in this flight control systems like?
No. Currently, what is the problem? What happened? I will tell. This is imported from the US. Suddenly, that company stopped the supply of this thermal management plates. Then finally, they want to indigenize it immediately. They came to us because we had been working on MMC. That's why we gone for indigenization. And now there is a UK company which is currently supplying. We do not know when, because all these strategic materials and common, suddenly they will tell, okay, this is the problem and all. And so that's why this is stopped. And the thing is that we cannot use any normal material as such. So we have to go for the requirement of this low CTE and high thermal conductivity is possible only by combination of this composite material. That's why it's special.
So this thing is having better thermal conductivity than plain copper kind of?
No. Copper is having 400 watts per meter Kelvin. It is not, because these two combination is required coupled with light weights. Copper is density is very high. I think three times of this one. So that's so all this combination matters. Apart from that, now we are working on aluminum magnesium scandium alloy with NAL, mainly for this aircraft fuselage structures, and the project is initiated very recently, and maybe in another couple of years we will be coming out with the rolled sheets. That is also again indigenization program. I think Sujata Madam is here, with whom we are collaborating for this indigenization program. Thank you.
So if there are no further questions, we will thank sir for a very enlightening talk. So with this, we come to the end of today's day, and I would like to formally thank Asha ma'am and Ranjan sir for their enlightening talk. Rajan sir, sorry. And I also take this opportunity to thank Sujata ma'am, who is the rapporteur for this session, and Aruna ma'am, DTS head, for being with us till the end of the day. And we request all of you to join us tomorrow sharp at 9:30, same place, and we will have some exciting talks tomorrow. So till then, have a nice time ahead.